Okay, we're going to look at section 6.4, volume by shells. I'm just going to briefly go over the motivation for this method and then a couple of examples. And then you have a few problems to do on MyMathLab and a little Instantake thing. So consider a region kind of like this. Now if we revolve this about the x-axis, we would be in pretty good shape to use our disk method. That would work. Revolving this about the y-axis, however, we have some issues. So basically what we'd have to do is divide it into two regions, because cross sections up here at the top look different than cross sections do down here at the bottom. Because here you end at whatever this function is and start at this line, and here you start at this line and end at this line. So you'd have to do this in two separate integrals to do it with our washer method. Whereas we're going to look at a new method called cylindrical shells that will work here. So basically the idea is we're going to make little rectangles. This is calculus. We love little rectangles. So if you pick any place here, you make a little rectangle. Then we're going to revolve that little rectangle around and find its volume. And then we're going to do the thing where we just sum up all of those volumes of those cylinders, and we'll have what we want. So that's where we're going with this. So you pretty quickly end up, if you want to read this, you can, with another integration formula. So this time our volume is going to be based around the volume of a cylinder formula. So we have 2 pi x fx minus gx. And you can see where the breakdown of that comes from. The 2 pi x part is the circumference of each one of the shells. The height of each one of the shells is fx minus gx. And then we have our little delta x over here. That becomes our dx, and that's like the width of each one of the shells. So we're getting the volume of all these little shells, we're adding them up. That's exactly what we're going to do in our integral here. So like I said, this gives us an easier way to do the volume of some shapes. It's worse for some, better for others. That's just kind of how these things work. So we have another method in our toolbox. So we're going to look at two problems. Oh, by the way, this section, this part where it says restoring order and then goes through some examples, this is probably pretty decent in giving you an idea of like which method should I use. And these methods are all kind of available, so you can look through example 5. It's probably a good idea. Just kind of think about, well, which one do I want to try to use? What's going to work best for this situation? And in general, if you know both methods and you try to set one up and it doesn't seem to work very well, you can try the other one, right? And you generally know, well, do I have to do 2 integrals instead of 1? Usually that's not ideal, but maybe those 2 are easier than the one you have to do the other way. So there are reasons to kind of look and think about doing both. But we're going to look at 2 problems. The first one is number 9. So here we have this region bounded by y equals 3x, and then y equals 3 and x equals 0. And they want us to use the shells method. So I've done number 9 over here. So we have our formula. Volume is integral a to b of 2 pi x fx minus gx dx. Here we're looking at bounds for x. And you can do a quick calculation. If y equals 3x and you want to hit the line y equals 3, that happens at 1. So we're integrating 0 to 1, 2 pi x, 3 minus 3x dx. Sorry, this got a little light here, but volume then would be 2 pi integral 0 to 1 of 3x minus 3x squared dx. So that's 2 pi 3x squared over 2 minus x cubed over 1 from 0 to 1. And if you evaluate that, you get pi. So that volume is pi if we revolve that thing around. Okay. Hey, my fingers are there. That's kind of neat. Next up, let's look at number 20. Here they want us to do this about the y. Sorry, we're revolving about the x-axis, which means we have to put everything in terms of y. So that's just like what we did in the last section. So for number 20, x equals y squared, x equals 4, and y equals 0, and we're going to revolve that about the x-axis. So again, I did this problem over here. We're just changing the formula. Everywhere there was an x, I'm going to put a y now. So I need to get these things in terms of y. I drew a picture. So x equals y squared, x equals 4, y equals 0. All of that is set up. This is our little region. We're revolving about the x-axis. And again, they want us to use the shells method. The first thing I did was I found this point up here. That is the point 4, 2. So we've got that. And then I need to get these things. Actually, everything is in the form that we need, right? So we're going to integrate with respect to y. So I'm going to take the outside function here, which is 4, and the inside function, which is y squared. And we're going to integrate 4 minus y squared dy, y times that, and we're integrating 0 to 2. That's our range on y. And you get 4y minus y cubed. If you integrate that, you end up with 2y squared minus y to the 4th over 4. Evaluated from 0 to 2. Well, the 0 part disappears. If you plug in a 2, you get 8 minus 4. That's 4 times 2 pi is 8 pi. Right, so there is that one worked out. Okay, that's going to be it for a video